Ever wonder how your computer can handle browsing the web, playing music, and running a dozen background apps all at once? Well, it all comes down to something called CPU scheduling. And today, we're going to start with the simplest, most fundamental method of them all. First come, first serve.
So here's our game plan. First, we'll start with a real-world analogy you already know. Then we'll dive into the actual rules. After that, we'll walk through a full example, crunch the numbers to see how it did, and finally, we'll talk about the one big problem that makes this algorithm so interesting to study.
All right, first things first. Before we get into any of the technical stuff, let's ground this whole idea in something we can all relate to.
I want you to picture this. You're waiting in line. We've all been there, right? At the bank, the coffee shop, the grocery store. There's this unwritten, universal rule about how it works.
The first person who gets in that line is the first person who gets helped. It's a simple, straightforward sense of fairness. And that idea, first in, first out, is literally the entire foundation of the first-come, first-serve algorithm. The first task that asks for the computer's attention is the first one to get it. Simple as that.
Okay, so we get the basic concept. Now let's put on our computer science hats and formalize this a bit. Let's talk about the core principles that make FCFS work inside an operating system.
So how does this actually play out inside your machine? Well, when a program needs to do some work, it gets into a waiting line called the ready queue. FCFS just looks at that queue and grabs whichever process is at the very front. It doesn't care if it's a huge, demanding program or a tiny, quick one. All that matters is who got in line first. And this brings us to a really, really important rule. FCFS is what we call non-preemptive. Think back to that grocery line. Once the person in front of you starts unloading their cart, you can't just shove them aside because you only have one item. It's the same here. Once a process gets the CPU, it owns it. It holds on until it is completely done. No interruptions, no cutting in line.
So when you boil it all down, the whole life cycle is just this simple three-step dance. 1. Processes show up and get in line. 2. The CPU grabs the one at the front and runs it until it's totally finished. 3. It moves on to the next one in line, and it just keeps doing that over and over until the line is empty. Okay, enough theory. That's how it's supposed to work. Let's get our hands dirty and see this thing in action. We're going to trace a few processes and see what happens.
So here's our setup. We've got 4 processes, P1 through P4. You'll see 2 key numbers for each. Arrival time, which is just when it shows up to the party, and burst time, which is how long it needs to run on the CPU. Let's map this out.
To keep track of everything, we're going to use what's called a Gantt chart. Don't worry, it's just a simple timeline for our CPU. So right at the very beginning at time 0, who's in the queue? Well, only P1 has arrived. So with no competition, it gets the CPU right away.
Now, P1 needs 2 units of time, so it runs and finishes at time 2. So what happens next? We check the queue. And hey, while P1 was busy, process P2 arrived back at time 1. It's been waiting. So as soon as the CPU is free, P2 gets its turn. It also needs 2 units.
P2 finishes up at time 4. We check the queue again and it's empty. Looking at our chart, P3 isn't scheduled to show up until time 5. So what does the CPU do for that 1 unit of time? Absolutely nothing. It just sits idle, waiting for the next job to arrive.
And right on cue, at time 5, P3 arrives. The CPU has been waiting, so it immediately starts running. P3 has a burst time of 3, so it will be busy until time 8.
And that brings us to the home stretch. At time 8, P3 finishes. Now remember our last process, P4? It actually arrived back at time 6 and has been patiently waiting in the queue. It's finally its turn. It runs for its 4 units, bringing us to a final completion time of 12. And just like that, we're all done.
So we have our timeline. We saw how it all played out. But was it any good? Was it efficient? To figure that out, we need to actually measure its performance using a couple of key metrics.
First up, we have something called turnaround time. This is pretty intuitive. It's just the total time a process hangs around in the system, from the moment it first arrived to the moment it's completely finished. We find it by taking its completion time and subtracting its arrival time.
Next is waiting time. Out of that total turnaround time, how much was just spent? Well, waiting. Waiting in line for the CPU to become free. The formula is simple. Just take the total turnaround time and subtract the time it was actually running, which is its burst time.
Okay, now we can fill everything in. We can pull the completion time for each process straight from our Gantt chart. From there, the rest is just simple math.
And notice something interesting. P1 and P3 had 0 waiting time. Why? Because the CPU was free the moment they arrived. But P2 and P4 had to wait their turn.
So let's step back and look at the big picture. We've seen that FCFS is incredibly straightforward, but as we're about to find out, that simplicity comes with a pretty significant cost.
On the one hand, you really can't beat its simplicity. It's easy to understand, easy to code, and it's fair in the sense that every process that shows up is guaranteed to eventually run. But, and this is a huge but, the average wait time can get awful. And it's all because of one notorious problem, the Convoy Effect.
That grocery store analogy is perfect here. Imagine you're in the express lane with just a carton of milk, but the person in front of you decides to do their shopping for the entire month. Everyone behind them has to wait and wait, even though their own transactions would be super quick. That's the Convoy Effect. A single, long process can hog the CPU, forcing a bunch of short, quick jobs to get stuck waiting in line.
So, to sum it all up, what do you really need to remember? First come, first serve is a simple, non-preemptive scheduler. It works exactly like a line at the store. It's super easy to implement, but it can be really inefficient. And its biggest weakness, by far, is that dreaded Convoy Effect.
This leaves us with a really important question. FCFS is fair, but it's not always very smart or efficient. What if we could break that first in-line rule for the greater good? What if we could somehow let the shorter, quicker jobs cut in front to improve the overall average for everyone? Well, thinking about that is exactly where CPU scheduling starts to get really interesting. And that's what we'll be diving into next.